Okay, well, that's a little bit of a welcome and a thank you to our sponsors that make this conference possible. So thank you to all of them, and thank you to you guys. Welcome to our 2025 Almond Conference. Very excited. This is the first session of what is a great agenda, soil and irrigation session. So hopefully you are in the session that you mean to be. So, there are other sessions going on. It's nice to see some familiar faces, some new faces as well. I'm Sebastian Saa. I'm the Associate Director of Agricultural Research at the Almond Board of California. Get the opportunity to oversee our production research program all the way from genetics to harvest. So it's super fun to be talking about different topics. And what it brings me today is about irrigation and soil management, a key topic in our everyday operations. And we all know how all that influence yield, influence our bottom line, influence our ROI. So we were working as an Almond Board very hard for this session all year round. And we didn't do it alone. We did it with our collaborators, with the speakers that you see here. We have a lot of new resources that we're going to bring to you. I put 4 new resources here at the back of the room. So as you leave, make sure to grab a copy, because what you're going to hear today is all new information, all new resources that we have developed for you. How we work for that? With these speakers. So we had the first speaker, Culumber. She's going to be talking about soil management. And coincidentally, she's the author of this soil management resource. Okay? We then will move to Guillermo, who's going to cover a lot about soil sensors. You know, I realized that over the years we talk a lot about plant sensors, maybe remote technology, but we haven't talked in a while about soil sensors. So Guillermo is really going to cover, based on his experience, the pros and cons of different soil sensors. We'll then move to Tom Devol, who's going to talk. Sorry, and by the way, Guillermo is from Wisconsin, and Tom Devol is our independent consultant in irrigation, probably a person that is familiar to you. He was one of our co-workers at the Almond Board in the past, and he has worked in the space of irrigation and automation pretty much all his professional life. So very happy to have him here as well, with the authorship of these 2 other new resources for you guys to pick up as well here at the end of the session or at the booth. And I figured that I have a slide about this. Yeah. Okay, sorry. There. So again, 2 resources. One is about automation. We talk a lot about the benefits about automation, but we haven't written them down, and the pros and the cons and the ROI. So I think this gives you a really walkthrough what you gain, what is the new things, what you may gain in automation. Also, we realize that a lot starts with irrigation design. And the critical questions or the hard questions, it should be discussed then rather than later in the 20 years of our life, of an orchard life. That is the best opportunity to discuss improvements in irrigation design. And we develop a guidance for you as growers to talk with your designers and ask those questions, take notes, and make sure that you're covering all the way from efficiency, pumping, electricity, to the ability to include telemetry, maybe now or maybe later. So lastly, we'll move to talk about our research project that we have been funding in this area to answer one of the simple questions but hardest questions to answer: how much water to apply. We all are familiar here with our ETC method, the cultivar evapotranspiration, but we're trying to move farther and create a new method, which is the actual evapotranspiration method, that may be complementary, at least also improve our efficiency. We develop a new guidance that I have here that explains the difference, the basic difference between ETC and ETA. And the research that is behind that is going to be presented by one of the lead researchers, Knipper, from the USDA ARS research team at Davis, where we have a project called the T-Rex. You will hear about that today. You will see it in the poster sessions, and they're going to be around for asking questions. With that said, I'm going to move to another part, which is the QA question of the session, before I pass it to the speakers. Again, 4 new resources that you see here at the left, a QA code that you see there at your right. Please, everybody, take a picture of this QA right now. This is the QA code that will allow you to ask questions during the session. We have a facilitator. This is different from previous years. This is a much efficient, much faster way to ask questions. We have a person that's going to be looking at those questions online as you submit them, and we will have time to answer them at the end. So take a picture now, open that form, and whenever you feel the need to ask a question, answer the first question of the form. There are more questions than just one. The other ones are for feedback about the session. So when we are done with this session, I also invite you to answer the last questions as well. If you have more than one question, after you submit the form, there's an opportunity to click again and submit another question, unlimited. So if we don't answer them all now, we will make sure to follow after, or we'll try to address them in our different communication channels. So this logo, this QA code, you will see it now. You will see it in the transitions slides of the speakers, as well as at the end. With that, I don't want to steal more time from what we have, because again, we have a lot of good resources and a lot of very good speakers that put their brains together to help us today. So May, you're next. Thank you.
Thank you, Sebastian. Nice to see you all this morning. So I'm going to be covering the soil management resource. And so, some of the questions that you might have are, why do we need to manage the soil? And, well, we need to manage to potentially reduce the erosion, enhance drainage and infiltration, but then simultaneously boost the retention of moisture in the soil. We want to increase the nutrient availability. If we're dealing with salt issues, we want to see if we can mitigate that. And then ultimately, we want to create an environment that's good for tree roots. We want to enhance and sustain the long-term yield of our orchards. So when we think about the soil in terms of the profile, it's not consistent throughout the root zone where the tree expands its roots. There's layers of different texture, color, chemistry, and biological activity that it's important to understand for so many aspects of management. And if we think about dividing this into sort of two categories, we can think of the soil in terms of the topsoil, the top layer where most of our organic matter accumulates, where most of the biological life is, and the nutrients that are needed for growing our trees. The subsoils are these deeper layers, and they're often more important for understanding how it controls the flow of water through the soil system and how well roots can penetrate. So the majority of our roots are probably going to be in the top 3 feet, but a portion of that could be that subsoil, and so we want, if we can manage it, create conditions that are conducive for root penetration down through that subsoil. And so when we talk about these different soil layers, there's a lot of different different forms in terms of the structure they can have, or aggregate or structural forms. And so this also varies with the topsoil down through the subsoil. So in the topsoil is where we tend to have granular aggregates that are more loosely arranged, and that is where water can more easily infiltrate down through the soil. Now, depending on how it's managed, we can also have a platey structure to the soil. So if there's a lot of compaction or surface crusting from, if there's a chemical influence that causes sealing at the surface, we can also have that platey structure. And then in the subsoil is where we tend to see what we call blocky or prismatic type structures that can have strong angular, larger clumps of soil. And a lot of this is largely dependent on soil texture. And so with the soil texture, that also is going to vary with depth in the soil. You may have different texture in the topsoil compared to what's in the subsoil. And so, I'm sure many of you have had your soil analyzed, hopefully with depth through the soil, so that how it's characterized through the entire profile. You may be familiar with the soil texture triangle. So if you have your soil analyzed, it'll tell you in percentages how much sand, silt, and clay. And that diagram shows you just the huge difference in particle size that we have between them. And so having an understanding, if you have predominantly sandy soil versus clay, has huge implications for both your nutrient and water holding capacity. And so a single particle of clay or sand is about at least 2 orders of magnitude larger than the largest particle of clay. And so cumulatively in the soil, if we're thinking about surface area for holding nutrients and water, you're actually going to have more surface area in that clay textured soil. And so again, that plays an influence on your water and nutrient holding capacity. And so depending on that composition, the percentages of sand, silt, and clay is going to affect how the soil aggregates together. And so, but in addition to that, we have to consider how much organic matter there is in the soil. And the reason, the importance for organic matter is that it controls the ability for the soil to form pores of different size. So we have both macro and micro pores. So the macro pores are what allows water to infiltrate and percolate through the soil. But then those micro pores are what allow for water to be retained. And so, you know, this is one of the key fundamental factors of, you know, a well-functioning soil, is that it both retains and infiltrates water. The soil, a well-aggregated soil, also supports a life, as I mentioned, in the form of organic matter, which could be plant residues, it could be, you know, roots from the tree roots or from cover crops, and then soil organisms, and their exudates. So there's many levels to this organic matter, and the way that cycles through the soil is largely dependent on the soil, what we call the soil food web. And so this says meso and microfauna. It should really be from macro to microfauna. So there's generally considered like 3 categories of these soil microorganisms that help with the turnover and decomposition of organic residues as they enter the soil. Okay, and so these residues, they provide energy to these organisms. So on a microbial scale, they use this as a source of the carbon in these residues as a source of energy. And then those microbes can provide food for the larger organisms going up the chain. And so together, when, you know, these organisms excrete, you know, they poop it out, the residues from that digestion. They're creating like this glue that holds the soil aggregates together. And so, but the quality of the organic materials is also playing an influence on how it functions in the soil. And so there's going to be a different balance of carbon to nitrogen depending on what type of amendments you're putting in the ground. And you know, these again provide key elements to sustain biological activity and growth that form that structure in the soil. They can protect the soil at the surface, physically protect the surface from the impact of, you know, extreme weather events, heavy precipitation. They can enhance soil water holding capacity for the reasons I just mentioned. And then they can also provide a source of nutrients that could potentially substitute for chemical fertilizer without compromising yield and revenue. And an example of that could be the use of almond hulls and shells. So there was a recent study out of UC Davis with a student, Ellie Andrews. She worked with Satdar Shan and Patrick Brown, and they looked at comparing the use of almond hulls and shells with potassium sulfate-based fertilizer. And so the graph on the left shows the amount of exchangeable potassium in the soil. So they compared over a period of, I think, 7 weeks. And so they looked at a control with no amendment applied. And then they compared an amendment with hulls, a mixture of hull and shell, and then shells by themselves, and looked at how that affected the available potassium in the soil over time. And so basically what they found was that there was a higher level of exchangeable potassium in the top 6 inches up to 7 weeks after application. And then they also followed the potassium nutrition in the tree leaves. And they compared that with a potassium sulfate control, and basically found that the potassium levels in the tree leaves were the same when they applied the hull and shell, actually the hull and shell mixture, and then hulls and shells on their own. Similar potassium levels in terms of nutrition. So, in theory, like, you could use some of these types of materials, maybe hulls and shells, maybe compost, to potentially offset your use of synthetic fertilizers. So I put together 2 tables here just to give you a budget idea of what your inputs would be and needs would be in terms of nutrition, and then what your cost would be per acre for that budget. And then if you were to supplement that with compost or these hulls and shells, how that would compare. And so what this requires to do this is to get a nutrient analysis. So in terms of nitrogen, like, I'm not really talking about a very big replacement here, but potassium, there's a lot of value in these hulls and shells and compost as well in terms of potassium as a fertilizer replacement. And so, just looking at if you were to apply a manure compost at 3 ton per acre rate and almond hulls and shells at 2 ton per acre rate, and you take a sample for analysis and find out what the percentage of your potassium oxide and your total nitrogen is, and then you need the dry weight percentage of that amendment, you can calculate what the nutritive value of that would be. And so as you can see, in terms of the annual cost per acre, it would be very similar, and potentially, applying the same amount of nutrients. And again, with the nitrogen, we need to be cautious. This example that I have here, you would assume that you would have a 25% availability of the nitrogen in compost. It may not be that high. And so you may not be able to cut your UAN necessarily as much. But you would, if you wanted to try this approach, you need to do leaf tissue sampling analysis, and you need to look at that from year to year. Of course, you need to look at your yield and how it responds. But there's potentially a lot of nutritive value in these amendments that you could offset use with. I do a lot of work in the realm of orchard recycling and looking at wood chips, and I do get a lot of questions. I know there's a lot of people that, there's probably a good majority of you in this room that have had some experience now with orchard recycling and replanting afterwards. And so, there's a lot of concern in terms of what is the effect of this really high carbon to nitrogen amendment have for the nutrition aspect of the following crop. So we've been following these. We've been following the effects of orchard recycling in a number of replanted crops. And what these graphs show, it's looking at the amount of carbon and nitrogen in the soil. And so this is what's called less than the 2 millimeter fraction. So this is the very fine particles of soil. So this isn't looking at, coarse wood chips. But we see very quickly, within a year really after making this orchard recycling application, that we're seeing increases not only in carbon, which is maybe something you would expect, but also total nitrogen. If wood chips have about between 40 and 45% carbon content, they have about a 0.02% of nitrogen, which sounds like not very much, but if you're applying 45 tons of wood chips per acre, that's probably several hundred pounds of nitrogen that's being mineralized, and it happens very rapidly. And so, because I get a lot of there's just this question that everybody has about immobilization, but what we're finding through our research is that this turnover with the addition of water. These graphs are comparing the soil chemistry both in the tree line where water and fertilizer are being applied, and then the alleyway. And so we're really seeing these dramatic effects where we're irrigating and applying nutrients in terms of increasing that soil and carbon nitrogen. 5 minutes. Okay. And so there's other indicators as well. Again, this one that says organically bound nitrogen proteins, I think is really exciting. It's in the bottom right-hand corner. So when we look at that total nitrogen as a percentage, a lot of it is these organically bound forms of nitrogen. So it's kind of like if you think about your nutrient stores in the soil, it's sort of like a bank account that's accumulating that you're getting from that rapid turnover of the wood chips. We look at infiltration. We've looked at other indicators, all seeing increases in biological activity in response to these wood chips. And then, of course, the thing that you're really concerned about is what does this mean in terms of growth and yield? And within the first year, in our trials, we found that the trees planted into wood chips compared to a control with no chips actually has more growth in the first season. And this is when we apply a targeted nitrogen to the root zone. So not enough time today to get too far into this, but basically we found that, generally speaking, you're using 3 to 4 ounces of nitrogen per tree to establish, depending on what time of the year. These trees in this trial were planted in April, and we only applied 5 ounces of N for the entire season, and we got more growth than the control in the first year. In terms of things like wood chips or the other amendments that I mentioned, they can have a really large influence on the water holding capacity. And so Tom is going to talk about with irrigation system design. A lot of times we would make those designs based on soil texture analysis. But if we're applying amendments that are greatly having an effect on the available water holding capacity, we might want to get some additional analyses to understand, how that may affect the type of irrigation system design that we're using, and then maybe irrigation scheduling as well. So, because with irrigation scheduling, we're trying to understand how many inches of available water there are per foot of soil, so that we understand how much we can irrigate in a single set, and then how long we can go between irrigation sets without stressing the trees. And since I'm running low on time, I'll just kind of cruise through this. There's so many different biological products out there that are available that promise to improve stress resilience, yield, your nutrient efficiency, enhance the soil structure, reduce your chemical footprint, and provide you with economic savings. There's a plethora of different products out there, and more field validation is needed to conclusively say what these do. And so it falls a lot on you, to do that research yourself. So you can do that through getting through these different soil evaluations that are laboratory type tests, and so that resource delves in more detail into all of these. But these would be the laboratory type tests. And then I'm going to talk a little bit about different field-based tests that you can use. But it all starts with the soil evaluation and knowing where to sample. So there's web-based resources that can provide you with a map to tell you about the general soil type changes across the field. It's helpful for you to identify where the suitable locations are to do a pit excavation to observe the entire profile. A lot of these maps are very dated, and it doesn't account for all the management that's happened over the decades. So they're really just kind of there to provide you a tool to understand where you should sample. But really, importantly, getting into the field methods, you've probably heard about the texture by feel method. And so when you're doing a soil pit, or you're having someone help you with a soil pit analysis, a lot of what is being done is looking at the soil profile by distinct layers and using this method. And so this table describes, just based on some characteristics like how well you can make a ribbon with the soil, if it feels gritty. Some indicators even use, sound of the grittiness in your ear. This same method is also used to understand what the water holding capacity is of the soil. So the resource goes into a little bit, this year in particular is where, would be a very sensitive time for being worried about soil compaction, because when the soil is at field capacity or more moist is when the soil is most vulnerable to compaction. And so something good to keep in mind. Infiltration is another method that's discussed, and this could be important to understand, how can you fine-tune your irrigation duration and frequency to prevent deep percolation? Maybe another important analysis before doing an irrigation system design. There's something called the slake test, something that you can easily do. There's a list of materials in the resource that just basically tell you, if you say you're doing a trial where you want to compare the effects of a biological over the course of the season and you have a treated and an untreated area, you could gather soil from both of those and make a comparison and see how well a clump of soil, how long it takes for it to dissolve. So in that image there on the picture on the right, you can see a soil that does not have very good aggregate structure. It just falls right through the sieve very quickly, whereas a soil with good aggregate structure maintains its shape and does not turn the water murky. You can do this is very similar kit that's available, commercial kit that looks at aggregate stability. Same principle, smaller aggregates. And then also there's a lot of commercial tools now available. If you have products that are promising to improve the biological function of the soil, there's some kits out there that you could use in the field that give you a really simple, quick answer to tell you, yes, you've increased your microbial biomass, yes, you've increased the fungal to bacterial ratio, and you just use a picture, you use your camera on your phone to help you with that analysis. And so, in summary, our soil characteristics, they change with depth, they impact the flow of water, air, and nutrients through their profile. And those field and laboratory assessments help track how management practices influence the soil function over time. Those organic materials, they protect the soil surface, they can help minimize disturbance, conserve moisture, and can improve that long-term soil function. And there is potential to offset your fertilizer use with a comparable budget. And with irrigation system design, you want to consider that soil infiltration and water holding capacity to minimize surface runoff and deep percolation to prevent nutrient losses. And again, all of these resources kind of reference different things to do with nitrogen, soil management, salinity management, and that orchard recycling. So I believe that you can find all of these in the back if you're interested. I'm also have poster number 37 if you're interested in looking at or talking more about our research in orchard recycling. So I'll be there at the poster session. Thank you.
All right, a lot of great new content, a lot of tests that you can do your own, all summarized here in this resource. Remember, if you have questions along the session, use this QR code to submit your questions. Well, now, without further introduction, let's start with Guillermo from WiseCon to overview of soil sensors.
Thank you, Sebastian. I'm glad May went before me because she explained. Now this is going to make more sense. When Sebastian asked me to talk about soil sensors and do an overview, I told him this was usually a 3 to 6 hour workshop, and he told me I had 15 minutes, so it's going to be tough. So I'm going to do a very 10,000 feet overview where I'm going to focus on one of several methodologies, one of several technologies to kind of like put a practical use case with sensors. But if anybody has any questions or wants to dive deeper on sensors, technology, interpretations, I'm going to be around today and tomorrow. Just come find me, or I just added my email there, g@wisecon.com. Please feel free to reach out and we can start a conversation deeper on soil moisture sensors and how to use them. So first of all, for us, soil moisture sensors are one of the key aspects for the water demand monitoring side of the water management cycle, to make decisions on how long to irrigate and how frequent to irrigate. This combined with other sensors, plant sensors, weather stations, irrigation information, satellite imagery. But at the end of the day, the weather station is giving us ETs, giving us rain, but the soil moisture sensor is showing us how the water is moving in the soil, how much water I have in the soil and how it's moving and how it's depleting. So it's a crucial part to make decisions on my irrigation scheduling. There are, and at the end of the day, the objective is to take this feeling, touch and feel, and the sensation, the noise. I had never heard about noise, but noise, I guess, and into a digital form, into basically taking that touching of the soil into something that can be interpreted and viewed on a digital mean, on a software, and potentially on a constant reading, not just the time I went out there and felt the soil. And there are several technologies. As I said, I'm just going to talk about the most widely spread out and used there. It's basically the water content or volumetric water content sensors that are electronic signals-based sensors. And then you have tensiometers that are measuring the tension in the soil. There's also other technologies like neutron probes and other instruments, but these are the most widely spread on the farms today. The tensiometers, it's a good tool, but all of them have pros and cons, as Sebastian said. Usually tensiometers are in the lower spectrum of price. Some of them are labor intensive. You gotta go put water on them for them to continue to work. Some are harder to get. I mean, there are some technologies out there like the ceramic tips that are available in closed protocol platforms, so they're not available to connect to other platforms. And in general terms, it's a sensor that works really good. It doesn't really need a lot of calibration. It's a nominal value that we're looking at here, centibars, so we know exactly what number when it's dry and when it's wet. It doesn't really show us a lot when there's saturation or when there's over-irrigation. So it's got pros and cons like everything in life. And then the other type of sensors are the volumetric water content sensors or soil moisture probes that are known in the industry, and they work through electronic signals. This one's the one I'm going to focus on this talk for a few minutes and kind of show everybody who's not. This is very basic, on how to use them and how to interpret data to make irrigation decisions. There are different brands out there. There are some that are probes, some that are what I call fork type that you need to dig a hole and install, but at the end of the day, they're all measuring water content. And there is a relationship between the two. This is important to understand. There is a relationship and there is a direct correlation curve between tension and water content, of course. There are different curves for different soil types, and this is where, especially people that work with soil moisture probes and the water content sensors, usually say I need to calibrate my probe to my soil. Usually they come pre-calibrated for most soil types, but it is true that you need to interpret the data a little bit different in order to make decisions in terms of time and frequency of irrigation, depending on your soil type. So the soil moisture probe and the capacitance probe is basically a sensor that works with electronic signals. It's measuring frequencies and times, and it's basically working around the dielectric constant. The dielectric constant of water, it's high, it's towards 80, and the soil and air, it's low, it's towards 0. So there's a direct relationship between a high dielectric constant and the water content. So what we have in the soil, it's basically soil, air, and water. And when I irrigate, I basically fill the pores of air with water, and my water content comes up. And the sensor detects this and shows this on the graphs. And of course, it allows us to see somehow when it's dry, when you are in that field capacity, and there is some oxygen, some air there, and then when there is saturation, where you basically don't have any oxygen in the soil. This is more related to what May was talking about. So at the end of the day, what we do, and depending, of course, as she was saying, what soil type you have, what water holding capacity you're going to have, what bulb shape you're going to have, and so that allows you to identify where and how you want to install the sensors in order to have good data for decision making. But what we're doing with the volumetric water content is that we have a sensor in at different depths. And what happens here is, as I was saying, when you have an irrigation event, what at the end of the day the sensors show you is that the water content comes up. So you irrigate, you fill those air pores with water, content comes up, then you have percolation, water starts drying out, and then when you see those staircases, it's what we're you're actually looking at day and night activity. So during the day, you have the roots drinking the water, then during the night, it flattens out, they drink a little less, and then when the day begins, they start consuming again. So you can actually see the velocity of water intake and the actual depletion of the water in the soil. And you can also identify the root presence. You can see where your roots are actively drinking water when you have different depths in the soil. So at the end of the day, what happens here is that we use different depths to identify how long we want to irrigate. So you run an irrigation, you can see the first sensors in the green, second purple, blue, etc. And you can see how when you run your irrigation hits first on the 6-inch sensor, then 10, then 14, 18, and you can see how long it took to get to 26 inches. And then you can also actually identify which depths have active roots drinking water. So now you tell me, okay, but on that last sensor, I don't have any roots. Okay, so then you don't want the spike on that. So you basically, this is a trial and error here. This is what I was saying before, the calibration, to identify how long I need to irrigate in order to fill my complete profile of active roots with water and not run longer than I should. If I'm spiking that last sensor, I might be wasting water. I'm irrigating below my root zone, or not run it short and actually stress some of the deeper roots. So it helps me to understand, to have eyes in the soil to determine how long to run my irrigation. Now, we like to put that sensor underneath the root zone. Usually we ask growers to put that sensor because that's my alert sensor. If I'm spiking that sensor in the deep soil, I'm irrigating too long, I'm wasting water, I'm wasting energy, probably percolating some fertilizers. And then when to irrigate. This is kind of like a decision that it's a little bit, takes a little bit more of interpretation in terms of understanding when I need to run my pump. I already know I need to run so many hours to fill my profile. Now I need to understand when I need to run it. Well, at the end of the day, we're also looking at this on the same dynamics the sensors are showing. When we see that we run the irrigation, we can see the percolation, then we can see the day-night activity. In this case, we can see the second day after irrigation was where we had the highest consumption, and then the consumption started shrinking. The staircases started getting smaller to the point it got completely flat. At that point, we know we're in stress, and the tree really doesn't have water to drink. Now, there are dynamics that show us that sometimes there could be a flattening out because it's raining or because it's cold. So this is important where we combine the soil moisture information with my weather information. So in this example, for example, we can see the day after the irrigation, the evapotranspiration was about 1/4 of an inch. There was a good consumption. 3 days later, same 1/4 of inch, no consumption. So we know the weather's there. We know the ET is there. The tree's drinking, but it's having a hard time to drink the water because the water's not available. So we should have irrigated already, basically. That allows us to calibrate my frequency and when to run my water. And of course, as May said, there are different holding capacities, so we will find there are different dynamics on sandy soils and on heavier soils. So a heavier soil might hold the water longer, might take longer to deplete, and the lighter soils will take shorter time to deplete. So on a sandier soil, you might be irrigating every day. You might be irrigating every other day. On a clay soil, you might be irrigating once a week. This is something you can calibrate. And of course, there are differences on weather, phenology stages that come into consideration. I said at the beginning, this is a 3 to 6 hour workshop. And then, well, here's the example. When you see that when the weather changes, when the tree starts drinking more water, when there's a higher metabolism, you will see that probably in 4 days you will deplete your whole tank as compared on a colder weather or on a lower metabolism week where you have maybe less fruit, maybe less development, maybe less canopy, and the tree will drink less water in the same time period. So this allows us to calibrate when to start my water and, as I said before, when to stop it. At the end of the day, the idea is to optimize your irrigation operation. That's why we say sensors go, the best way to work with sensors is to have them online, to have them with constant readings. We lose a lot of these benefits when we have a sensor out there that we gotta go out and download the data, or we go once a year to download the data to provide it to NRCS and not really make good use out of the data. Having them online gives you this constant information that allows you to make decisions and to optimize the irrigation. Important considerations, I'm just gonna run through this because of time. Soil, the proper installation, so it needs to be installed properly. with good contact to the soil. There are many companies out there that have experience on this, that have been installing sensors for years. They can help with that. Identify your soil type. May was talking a little bit about this. If you have a irrigation set that has more than one soil type, then you might want to identify your predominant soil type. Or we've had people that even install 2 sensors in one set and then irrigate both soils. So they do high-frequency irrigations for the sandy soil and some longer irrigations for the heavier soils. The right tree, it's important to identify and put this on the most homogenic part of the, like something that is representative of the set, of the block. We found cases like this one where this had been a tree that had a disease and was pruned back in the day, and they installed the sensor there, and it was the ugliest tree in the set. So, it did not look like all the rest of them. And also the distance from the emitter. If we're looking at drippers, we're looking at maybe 5 inches from the emitter. With working with fan jets, maybe 10 inches from the emitter. We want the probe to be where the water is. The roots are going to be where the water is. The sensor needs to be where the water is. That way we can do this kind of management. Ground truthing, very important. This is not magic. We need to walk the orchard. We need to ground truth this. There are some examples of people with sealed soils that are not getting good infiltration rates, and they put the sensor out there. The sensor is saying that it's wet, and you go out there and you see ponding. You need to walk the block. I mean, the orchard. This is, as I said, this is not magic. This is another tool on the toolbox, but it's important to ground truth it and always keep an eye on it. And keep an eye on the actual sensor. We've run into people that this is our navigation tool. We're using 1 sensor per block, 2 sensors per block to decide how much to irrigate. And if we don't keep an eye on it and make sure that it still stays a representative site, it might mislead us. And finally, complementary sensors. There is also, it is very important to complement the sensors with weather stations, evapotranspiration, of course, rain, as I mentioned before, leaf temperature sensors, dendrometers, flow meters on the main line, make sure the irrigation is there. So there's other sensors that need to be complemented in order to have a good picture of what's going on and then be able to fine-tune your irrigation decision-making. And with that, I'm done.
Thank you, Guillermo. Nice overview of the power of soil sensors. So let's now move to Tom. Remember, if you have any questions, you can take a picture here, or you can go to the link of the QR code and submit your questions. We're collecting the questions as we go. So now we move to Tom, who's going to talk about 2 new resources as well.
Thank you, Sebastian. Good morning, everyone. So I'm going to cover 2 new resources that were developed this last year. One on automation and one on questions to ask your irrigation designer. I really encourage you to grab these in the back, because I'm going to talk about the whys these were developed for, not the individual content in them, but why it was developed. You need to read them to find out the content. So let's jump in. So nice picture. Who's that ugly guy on the cover of that one? Who put his picture there? Anyhow, please pick these up in the back. But starting off with the irrigation automation. So really automation, if you think about progress that we've made in water efficiency, automation's our next step for an opportunity for improvement. So when you look at the history of and evolution of irrigation techniques, we kind of started off with dryland farming. I mean, really in the beginning, we just did what Mother Nature gave us. And then as time moved on, we moved into flood systems, really cost effective. We had the infrastructure in place to take care of that, simple to apply. But it really fell short in the efficiency in many cases. You had to have the perfect soil for it, at least in almond crops. Then we moved up to hand-moved sprinklers. And I think most people who have ever worked with hand-moved sprinklers are happy they're gone for the most part, because they were very high labor. But man, did they improve efficiency, right? They helped us improve efficiency, but we still had this thing where we're doing sections of the orchard, and that had an impact on efficiency. So we made the move to solid set. Another great evolution. and it really helped with things like frost protection. It was a real simple system. Labor greatly reduced itself because once it was installed, it was pretty simple to take care of. But there are still opportunities for efficiency gains. So we moved into drip and micro sprinklers where we're delivering water directly to the tree itself and not worried as much about the middle of the rows, right? Well, now automation is really that next big space for an opportunity to improve our irrigation. Now we're able to address things like when we're running water from an energy perspective. So it's not just irrigation improvements, but it's also energy improvements. So if you look at a pump station, it's kind of where everything starts in automation, is usually at the pump station. There's a lot of opportunities for other things, auxiliary sensors, like Guillermo was saying. What else can we measure at the pump station from things like our flow, our pressure at the system? But we can also control valves at the pump station. We can control fertigation injection at the pump station, as well as putting a master controller there to control things like our infield valves. So most things start at the pump station. And then just the guide will go through looking at this vast range of systems that are available to us. You can start off really simply with just using a simple time clock. You can go to a system that works at the pump station and controls a limited number of valves, to a system that's much more comprehensive, that does a vast number of valves, to a very complex system. So the guide will help walk you through, what's that look like? What would I be looking at to start off? And think through things like, today I want to do this, but I want to leave an opportunity to expand in the future. Am I landing on the right system that'll help me expand? Because a lot of growers, you'll want to start off simply in many cases, but do you have room to expand? Then the pros and cons. And the guide will walk you through, thinking through what are the pros and cons for different approaches to automation, and help you kind of answer those questions for yourself. How's this fit for me? And again, look at expansion. That would be a con. If you want to expand, but you're landing on an automation system that's very limited, there you're going to have to replace it to expand in the future. One place I think a lot of organizations miss is how's this fit in with the complete organization? I used to have growers come to me and the ownership wanted to put automation in or other field technology. They wanted to give the tools to their field staff to really improve their irrigation efficiency. But their field staff weren't able to manage that, right? So the owner had the best intention, but they didn't get the training for their field staff where they could really benefit from it. So sometimes they had field staff that were against it and didn't really support it. So the guide will kind of walk you through questions of how's this fit into each individual department within the organization so that you land on a solution that really meets the needs for the complete organization. And it's a place I've seen mistakes made that were really costly by not walking through that. Then return on investment, both for the automation system itself, for pump automation, valve automation, as well as for fertigation. Just questions to ask when you're looking at ROI. How could I do my own ROI internally? So the guide will kind of guide you through that process of how do I determine what my costs are, and is this going to benefit me long term? Is it going to cost me a lot? Is it going to end up profiting, bringing profit? And I think most growers find out these systems are profitable at the end of the day. They save you money. So it walks through all these different things. So I really encourage you on the automation guide, pick it up. It's pretty deep. So, and go through these. And then as we move into questions to discuss with the irrigation designer, when I was an irrigation designer, I ran into this a lot. Growers would walk in and say, can you design the irrigation system for me? And a lot of times the only input they would give me is, where the field was located and what their tree and row spacing was. And they didn't have a lot of questions beyond that. They kind of trusted me as the designer to deliver them the right product for them. But really, this is a 20-plus year decision. And so the board developed this, this resource to really guide you through what questions do I need to think about? How can I best be prepared when I walk into that meeting? And it's really laid out in that format where you can fill it out and take it into the designer. So to kind of prompt those questions for you. Because a lot of times you don't know what questions to ask, right? That's why you've got an irrigation designer. But the more you can lead that process, the better design you're going to end up with at the end of the day. So when you look at it, it's going to walk you through what's the plan. So from orchard planning, what's the orchard itself going to look like, to what irrigation method, frost protection, filtration, complicated issue. What kind of filtration do I want to do? And this can be a big cost swing between really simple filtration, if you have very clean water, to much more expensive. What's it going to cost to operate? Many times this is overlooked. And a lot of times designers don't go down this path unless they're requested to go down the path. But you can design a system around operational costs and save yourself money. Automation, do you want to put automation on it? And what would that look like? Are we designing it where I have the facility to put automation? It's as simple as a flow meter. A flow meter has very defined specifications at the pump that it requires to deliver good flow readings. If you don't plan for that, they're going to be digging up your discharge and lengthening the discharge later with a backhoe and more plumbing to address that flow meter. Address that from the get-go. Warranties, incentives, I'll get into a little bit more detail. So looking at orchard planning, here's a drawing of kind of a standard orchard. There's a lot of questions here. Do I want to irrigate by variety? If I have an existing flood system, is there a benefit to leave it in place if I want to do recharge potentially in the future? A lot of times those old flood systems are torn out, but there may be value in leaving that in place. I need drive rows. Where am I going to put my drive rows? Do I want to put a storage reservoir in so I can store my own water for times of frost protection? So things like that. The irrigation method, a lot of opportunities here to make mistakes and a lot of opportunities to find improvements. So what kind of system do you want? Where I am in the Durham, Chico area, solid sets are really important because we have frost issues. But could I put a drip system in if I am redeveloping an orchard that has an existing solid set, leave the solid set in place and get the benefit of solid set for frost, but then also have drip for irrigation? So kind of walking through questions like that with your designer. Filtration. This is a complex area, and it's good to kind of talk through what your options are for filtration, both in the ease of use and the way it manages different types of water. If you've got district water with a lot of algae growth, you may need a much more comprehensive filtration system than where we are, where I am, where we have very clean water and we're using solid sets. We can get by with very limited filtration. Big cost swings when you look at this. And this is the gift that keeps on giving. If you don't make the right choice with filtration, it will drive you nuts over the years. Maintenance, oh my word, it can be a nightmare if you chose wrong. Energy costs. This is a place very few designers look at. They may think about it, but they're not giving you the energy costs unless you request it. You can make changes in your pipeline sizing to reduce your friction loss that will, over the life of your orchard, save you tons of money in pumping cost. But what's that designer's, one of his goals is give you a really cost-effective system to buy the hardware, right? Because he's focused on delivering you a low-cost irrigation system. But he can deliver you an irrigation system, save you money on the original purchase price that for 20 years you'll pay for. in energy costs. So it's really important to look at what the energy cost is and ask the designer, can you do a cost analysis so I know, would it benefit me to size up? Would I be better changing a pump to a more efficient pump that may cost me a few $1,000s more to purchase the pump, but long term, it'll save me money on pumping costs. And then technology. In the previous talk, you looked at this. It's comprehensive, all the different things you can do in technology. There's a lot of options. It's good to think about this at the design stage. You may want to install some technology when you're installing the system at the get-go, but you want to make sure that, like putting the right valves in, maybe you don't want to automate valves today, but in 5 years you do want to automate valves. If you put the right valves in today, you won't be replacing them later with valves that can be automated. So just silly things like that, a mistake of not thinking it through that can really cost you. Warranties, often never discussed. And you really want to know what are the warranties on all the different components in that irrigation system. And they're different by company to company. And does that warranty include labor? If you had to replace all your sprinklers because there was a warranty problem on your sprinklers, but you have to pay the labor to replace all of them, it could be pretty expensive. So you want to know that up front. What's the warranties? And then lastly, incentives. And the Almond Board's done a good job. They have a website. If you want to capture this QR code, they have a web page that is really current on what current incentives are. And this is a lot of work to keep up to date on incentives, and this will really help solve that problem with knowing what current incentives are. And with that, I will pass it off. Thank you. Thank you.
So, excellent work so far, 3 speakers, a lot of work behind the scenes, as you can see, with the new resources. I'm really excited. That is where we are today after years of research and innovation. That is it today. What you're gonna listen now is maybe what is tomorrow. It's research that's going on, that is being led by Kyle and many others. And I'm very excited also to hear about tomorrow. So thank you, Kyle.
All right, thanks, Sebastian. Good morning, everyone. So today I'm going to be talking about T-Rex research updates and new irrigation management resources and the use of actual evapotranspiration in terms of, or in comparison to crop ET. So for a quick background, the T-Rex project started in roughly around 2021, and the idea was to develop a satellite-based ETA toolkit for irrigation management within an almond system. And since 2021, it's really built and expanded from that initial idea into 3 different scales that we're doing research in. So we have everything from the tree level up to the field scale level and regional that includes the satellite-based estimation. So what we really want to do here is understand what's happening at the tree level, at the field scale level through like UAV research and the like, and have that information inform us on what we're doing regionally with our satellites, not only to validate our products that are being developed, but also hopefully improve. And again, always with the idea to create an irrigation decision support tool. So everything is related to water in this research project. So over the years, there's been quite a few peer-reviewed research articles that have come out of the T-Rex project. Most notably, we published a paper on an economic analysis of converting from an ETC-based irrigation approach to a satellite-based ETA approach, and the benefits of doing so. We also did a thorough evaluation of the OpenET product in almond orchards throughout the state of California. That was published just last year. But right now, our current focus is on improving these remotely sensed modeling approaches, specifically in almond orchards. So think less of an evaluation of how things are going and how things are working in almond orchards and how we can structurally change our modeling approaches to better understand or to better model ET within an almond system. We're also working on forecasting actual ET out 1 to 2 weeks. This has been a topic of conversation the last few years with the almond industry as well as other industries, and really wanting these forecasted products available more operationally, also to help with irrigation management. And then ultimately delivering this information to growers through early adopters. So instead of sitting in our offices working on this research after the growing season, reconvening and talking about it, we want to put this information into the hands of growers in real time so we can better communicate what we're seeing and what they're seeing in their orchards. So in terms of improvements, we have a postdoc researcher, Karim Meza, who is in our group. She's working on integrating a physiological model within our energy balance ET model. So what she's working on is creating a temperature correction that's based on physiological measurements like leaf temperature, somatoconductance, and net photosynthesis. So we can have a better idea of what's actually happening at the tree level to improve our, in this case, UAV estimates of thermal imagery to get ultimately a better ET estimate. So what you see here is a UAV imagery of one of our almond sites. On the right is an RGB image, or on the left is an RGB image. On the right is an uncorrected land surface temperature. Now, what Karim is doing is using a classification segmentation model to partition a tree, a shadow, cover crop, soil, so we understand specifically what is an almond tree in our imagery. And in doing that, we can get an actual canopy temperature and soil temperature. And when we know our canopy temperature, we can directly apply that physiological model, correct it for what we think is happening at that tree level, and ultimately improve our ET estimates. So on the left is a plot of observed energy balance components on the x-axis, modeled on the y. On the left would be business as usual, uncorrected temperatures. On the right is applying this physiological model. And there's not a lot of shift happening, but we do see a decrease in our mean absolute error of about 18% when applying this model that Karim has been working on. So now our priority is understanding this a little bit better and how we can transition it to a satellite level. And we can scale this up, not just within a single orchard, but over a ranch and ultimately the Central Valley. Something else that Karim has been working on, this is a little bit more recent, but is evaluating crop coefficients and the different energy balance closure adjustments and how they affect those crop coefficients. So there's a lot of different ways to measure actual ET within a cropping system. So what we want to do is look at all those different methods, all those different closures. We want to use all the information that we now have from the T-Rex project and try to get a sense of what the uncertainty is in these crop coefficient estimates, how they compare to actual ET, and how they might be able to be used together to map stress and crop water use in an almond system. Now, on top of improving ETA, we're also working on trying to understand the independent impacts of meteorological parameters on GPP for different crop water stress scenarios. So when I say GPP, I mean gross primary productivity. This is how fast trees are turning sunlight and CO2 into sugars through photosynthesis. So think carbon into your system. That carbon is what is being used to build the wood, leaves, and ultimately fills the nuts. So when weather or stress slows GPP down, you're potentially or effectively shrinking your potential for yield. So when I say scenarios, I mean these different binned scenarios of a meteorological parameter. So here, what I have highlighted is shortwave radiation into your system and a crop water stress index on the Y. and you can see a few others there like air temperature, VPD. And what we want to see is that scenario, that combination of those two things, and effectively how it's changing GPP estimates. So green, positive, purple, negative. And ultimately, we can get a sense of which binned scenarios cause positive GPP, a situation that we would like to see in an almond orchard. And ultimately, what you can see here is the meteorological parameters that are having the largest effect are, VPD, air temperature, and to a lesser extent, shortwave radiation. These are easy parameters to obtain. And we can model crop water stress index from a satellite perspective. So the idea is, through modeling crop water stress index, obtaining fairly simple meteorological parameters, we can hopefully get a sense of GPP sources and sinks in real time and potentially develop management strategies that could nudge GPP in the positive direction. Now, to forecasting, so again, this is something that we've been working on for a little while now. Apoorva Jha is a PhD student working with us, and she is currently about to publish her first study looking at using a univariate deep learning model to forecast out actual ET in almonds as well as olives and vines. And what you see here is the results of that study. The dark brown bar charts there are Apoorva's deep learning model forecasted error, and the lighter brown error bars are using like KC values and a forecasted reference ET to get ETC error. So there's still room for improvement. We're working on that, but the errors are going in the right direction, which we are happy to see. Now, note that this is a point-based forecast, so it's only like 1 pixel forecasted out in time, and it only uses OpenET data as input. So it's kind of like a large language model, like if you're typing a Google email or Word, or on a Word document, and it fills in that next word. This is working kind of in the same way, only instead of the subsequent word, it's choosing a subsequent ETA value out 7 to 14 days. Easy to implement at the point scale, but now we're trying to transition and do this at a spatial scale. It's proving to be a little bit more difficult. So the spatial maps that you see there on the left is a modeled ET product from Dyslexie, so a satellite-based ET, and on the right is Apoorva's forecasted ET over the same period. What you would want is to see those magnitudes and spatial patterns look exactly the same, or at least close to the same. So again, we still have some room for improvement here. We're still actively working on it. We're having to incorporate additional spatial products. So instead of just using OpenET like we did before, we're incorporating NDVI imagery and other meteorological parameters to help with that forecast. But ultimately, we do want to keep these models light. We don't want to have a ton of input into them because we do want to use them operationally. So the simpler that they are, the less input required, the better for us, and the easier to implement operationally. So this lands kind of on the last point that I want to talk about, which is this delivering of information. So we recently started a wavelet evapotranspiration tower network, and the idea here is to connect our satellite-based remote sensing techniques with tower-based estimates. Normally, our research-grade towers are quite expensive. They take a lot of maintenance, and it's just not entirely feasible to have that type of sensor set up all across the state of California in multiple ranches. So what some of my colleagues have done at UC Davis is they've created this wavelet technique that uses much cheaper sensors to ultimately derive an actual ET product. And if we have that actual ET product on the ground within like a ranch, we can use it to bias correct and kind of ground our satellite-based ET estimates. And with that grounding, we can have a higher confidence in irrigation recommendations that we would ultimately be wanting to make for our grower. So we've developed a dashboard to share this information with our early grower adopters. So here you can see the landing page in a ranch, and a grower can hover over that ranch, select a field of interest, it provides the suggested irrigation amount, what it was last week. You can see the site ground adjustment there, so that's going to incorporate that site, that wavelet tower on the ground, and as well as different parameters like depletion targets, where they were last week, actual ET and reference ET. And I'm not sure if the video
Should play. Click again.
Oh yeah, there we go. So it's very interactive, but I want to preface this with saying that we are not dashboard creation people. We don't have the bandwidth to do this. We're not software engineers. There are a lot of people in this room, including Guillermo, who are much better at creating much nicer looking dashboards. The idea is simply we want to be able to communicate better with our early grower adopters to get a sense of what information is important to them and what information is important to us. So what can they provide us operationally that can feed into this app? So you can actually, like a grower can actually go in here and select a cell and input their irrigation, what they irrigated last week. That'll update all the depletion records and will update suggested irrigation amounts for the subsequent week. So again, this is more of like a communication tool, so we can better understand how our approach is working and what we can do to improve it, how we can do to clean it up, and ultimately hand that information off to someone that is much better at creating dashboards and recommending irrigation than us. And also, our early growers have been really good to us in allowing us to set up all this research equipment in their fields. So we thought it's about time that they are able to access that data in real time, and if they want, use it for their management strategies. So I always like to end on this because there's a lot of work being done by a lot of great people within the group, not just me. So a big thanks to them. And again, if there's any questions or wanting a better understanding of the differences between actual ET and crop ET, the resources are again at the back of the room. And I'm also happy to take any questions after the session. Thank you.
Thank you, Kyle. Very good flavor of what's coming next, and I think it sounds a little bit complicated, but then we simplified in the last mile to bring something new to you. The best we have today to define how much to irrigate is the ETC method as a starting point and all what the other speakers cover. Hopefully tomorrow, maybe not tomorrow exactly, but in the next 5 years or so, we can have the ETA method as a new tool that can help you to identify exactly how much your trees are transpiring in situ, in your sites, in your orchards, rather than using referential values. So thank you for sharing all that today. We are going to allocate 5 more minutes to this session. I know we are over time, but we have gotten multiple questions. Danielle, my coworker, who's going to help me to moderate the Q&A, is going to take it from here.
All right, thank you, Sebastian. So we have 27 questions so far. Thank you for everybody for submitting those. And we're gonna be obviously not getting to all of them, but we'll be using that to help guide our future communications and outreach. The first question I'm gonna answer actually is, will the PowerPoint be made available? Yes, the PowerPoints go online at ammons.com or ammons.org/conference, and there's a section there. They'll be up in a week or two. The first question, May, for you that I'm going to ask, how much influence do you think improved soil biological activity has on water infiltration and holding capacity? And are you seeing measurable reductions in runoff when biology is part of a soil management program?
Well, for an example, with orchard recycling, we have been looking at infiltration rates, and especially when you first initiate it, there's a huge impact on infiltration. And so, and I think that would be true with a lot of the other amendments as well. I haven't directly measured it, but I would think the same would be true for anything that is providing a mulch on the surface of the soil is likely going to help with infiltration and help reduce runoff, because it's protecting the, it's absorbing that energy of the impact of the moisture hitting the surface, and then allowing the water to more slowly percolate through the soil.
Great, thanks, May. I'm going to do one per speaker. So Guillermo, I have you next, and I've combined a couple questions. There were some definitely about sensor placement and non-homogeneous orchards. So what is your recommendation for placement in like a solid set orchard or maybe a flood system? How about placement in comparison to the trunk instead of the emitter? Like, is there anything relevant there? And then the general number needed per orchard or block.
Yeah, that's a tricky question because it depends on your irrigation system, your soil type. So usually what we recommend is, of course, one per crop, first of all. Age of the crop is also variety, might be, it depends at the end of the day how much money you want to spend on sensors. You can get a pretty high accuracy by putting more sensors. In terms of the actual location, it depends also on the methodology you're going to be using. The one I showed is pretty much tied to the actual root consumption. So you want to be on that root bulb, which is where you're going to have your irrigation, your emitter, basically putting the water out. So with solid sets, you may want to be a little bit farther from the emitter, maybe 18 inches. With micro sprinklers, you're around 10. With drip, you're 5. So basically getting closer to the water bulb for the methodology I showed is the way to go with the actual sensor placement. And then one per soil type is usually important. If you want to go with only one sensor, go with the predominant soil type, and then you can get deeper as you talk about species, crop, age, varieties even. So depends on how much money you want to spend.
And one per valve too, maybe?
Well, one per set at the end of the day.
Mm-hmm.
Because at least you're going to be the minimum manageable block at the end of the day. Like if you have one per valve, but you irrigate 4 valves together, you can't really split your irrigation system.
At least one per management unit. Then.
Yeah, one per management unit. That's ideal. But there's also ways where you can go with less than one per unit and just go one per soil type. And you define your strategy on frequency and duration of irrigation per soil type, and then you replicate that decision based on that sensor on all your soil types in the ranch with that soil type.
Got it.
Making sense? So, and if you've never worked with soil moisture sensors, I usually recommend start with 4 is the magic number. Don't go more than that. Understand how to use them, get the feel of it. I've seen people go in and dive in and they spend the money on 30 of them, and then mid-season they are completely overwhelmed with the data. So it's important to start small, get comfortable, and then start, growing from there.
Got it.
All right, this one's for Tom, but others might have thoughts too. Should we be thinking about irrigation strategies to develop deeper root systems, and what would those be in terms of soil health and water application?
Well, of course, and that's a conversation again to have with your designer. Am I designing a system that'll give me that flexibility? If I want to drive water deep, can I drive water deep? Can I run water that long? So this is where I think any strategy you have, you need to lay that on the table at the point of design, because like I said, it's a 20-year decision. If you make a decision that's going to tie your hands on what you can do, it's going to be expensive. So absolutely, yeah.
Thank you.
All right, and last one for Kyle. How do the wavelet towers differ from existing commercial towers, ET-based towers like Thule?
Oh, that's a good question. My colleague Nico would probably be the best one to answer this. You know, I don't know if I can give you an honest answer or know the difference, and I would hate to say the wrong thing for the wavelet. But it is based on what Thule's approach has been in terms of wavelet. But I believe that there are key differences specifically as it relates to measuring like net radiation and ground heat flux, which are two other components on top of the sensible heat flux estimation required to ultimately back out ET. So in short, it is a refined methodology that we're currently testing.
And the Thule technology, the patent technology, comes from this research team. I mean, Andrew Macaron is also was a former professor of Tom and others that developed Thule. So there is also
Tom
base research that started there, and you guys continue the research, and the other branch went commercial. But I think it are interconnected, and what you're doing builds from those early discoveries.
Yeah, Tom was one of Andrew, who is in our group, one of his first postdoc students, and Andrew is actually on the patent for Thule. So, yeah, they've kind of carried on that methodology of estimating ET through the wavelet approach.
Mm-hmm. Well, great. Love the session, love the contents. Thank you very much, everybody. Let's finish with a round of applause to our speakers.